Colligative properties. You guys ever made ice cream? Some of you have. Well, if you haven't, we're going to do that. I think it's next week in lab, and yes, we are going to eat it. Use an old-fashioned ice cream maker. It's got a bucket and then a thing on the inside where you put all the ice cream stuff. And inside that bucket you put ice. But if you just put plain ice, the ice cream will never freeze. You have to add salt to the ice. The reason we add salt to the ice is that it lowers the freezing point of the water. It causes the salt causes the ice to get colder. And so instead of being at 0 degrees Celsius, you can get it down to around minus 10 degrees Celsius just by adding salt. This freezing point depression is one of the colligative properties. These are properties that depend on how many particles there are dissolved in the solution, not on what those particles are, just how many there are. If your solute is an electrolyte versus a non-electrolyte, it will have a slightly different effect because when an electrolyte dissolves, it forms ions. It may form 2 ions or 3 or 4 or 5 ions. When a non-electrolyte dissolves, it only forms 1 mole of particles for every mole of substance. And so we'll look at that difference later on. So vapor pressure lowering is a colligative property. The vapor pressure of a solution that has a solute in it, a non-electrolyte, is lower than the vapor pressure of the pure solid. And here we're looking at non-volatile solutes. So like if you put salt into water, it will reduce the vapor pressure of the water. And we can understand this by looking at the dynamic equilibrium established when we have evaporation. We have the gas and the liquid state in equilibrium with each other. The rate of evaporation depends on the surface area, among other things. If you put a solute in there, that's going to take the place of some of the water molecules at the surface and effectively reduce the surface area. It's going to slow down the rate of evaporation. So now the rate of evaporation has slowed. The rate of condensation depends on the concentration of the gas particles. So this will remain at its original rate, but then the concentration here is going to be decreasing, and so eventually it will become the same as the rate of evaporation, but they're both smaller now, and so the vapor pressure here is lower. Does that make sense? This is a crazy thing. So here we have a closed system. This is a cake plate. We had 2 beakers, one with pure water, one with salty water. You leave them alone for a while, and this may take, it's hours at least, might take days. You come back, and the level of the water in the pure water beaker is lower, the level of liquid in the saltwater beaker is higher. That's crazy. Water moved from one beaker to the other. There's no tube or pipe or anything. Well, how did it do that? It went through the air. The water is evaporating from both of these solutions, right? And it's going to establish a vapor pressure inside this container. And some of those molecules are going to be recondensing as well. What's different about the salt solution is that the addition of the solute reduces the rate of evaporation. And so the rate of condensation is the same as in the other beaker, but because the rate of evaporation is less, the level of this solution will rise. And if that rises, the other one has to go down. So we can understand it that way. We can also understand it in terms of an increase in entropy. This tendency towards mixing, which we saw with, I'm talking about the gases mixing, and here we have the vapor water vapor. I don't know where I'm going with that sentence. We have this solvent in the concentrated solution, in the pure solvent mixing. They're naturally going to mix to form a less concentrated solution. I think of it as nature's like, there's an imbalance here. This one's different than that one. We want to make it the same, right? Everything wants to be the same. And so it'll try. Any questions? So of course we can quantify this. This is Raoults law. So the vapor pressure of that solvent in the solution is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. And this vapor pressure needs to be at the same temperature that you're looking at this. So the vapor pressure is directly proportional to how much solvent is in the solution. And we can measure vapor pressure lowering, delta P, as being chi solute times the vapor pressure for the pure solvent. And if you're interested in how they got from here to there, I'd be happy to show you later. So we can do a problem like this. Calculate the vapor pressure at 25 degrees C of a solution containing 55.3 grams of ethylene glycol, 285.2 grams of water. The vapor pressure of pure water at 25 degrees Celsius is 23.8 torr. So they're asking us to calculate the vapor pressure of the solution. So we need Raoults law. So the vapor pressure of the solution is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. So they gave us the vapor pressure of the pure solvent, and this is at the same temperature that we're looking at. So this is P0. We're trying to find this. We've got this. So we need the mole fraction. Well, we just learned how to do mole fractions. So the mole fraction of the solvent, actually, I'm going to go in here. Oh, whatever. My eraser was a lot bigger than I expected. The water is our solvent, so I'm going to use H2O there instead of solvent. So mole fraction of water will equal the moles of water, the part over the whole. So down here we want the whole thing, moles of water plus the moles of the solute. I'm going to call it EG, short for ethylene glycol. And they gave us masses, but we should be good at converting grams to moles by now. So a mole, and for water it's 18.02 grams. Clear the calculator. 285.2 divided by 18.02. 15.8 268 moles of water. So that goes into this equation. And we need the moles of ethylene glycol. So 55.3 grams. We're given the formula there. that formula is suggesting how it's connected. We could condense that and say, well, that's C2, and 2, 4, there's 6 hydrogens and 2 oxygens. That'll make it easier to calculate a molar mass. Two times 12.01 plus 6 times 1.008 plus 2 times 30, not 32, 2 times 16. I'm getting 217.556. Anybody else? One way you can stay awake is by actually doing the calculations with me. I think that's right. So 55.3 divided by that, 0.254. That's our 3 sig figs and then 1/8. Anybody check my math? You got 62? I've got a times in instead of a plus. Yeah, 62.068. Thank you. Thought that seemed not quite right. 62.068. .89095. There. So that is the moles of our solute, so we need to add that in here. That's moles. The mole. Come on. The mole units cancel out. Be careful when you're doing the math here, because you don't want to miscommunicate with your calculator. So I take the numerator and I'm going to divide by the denominator, and I'm going to use parentheses. I'm getting 0.9467. Zero. Anybody else get that? Okay, fine, whatever. Is that a reasonable mole fraction? Mole fraction should be between 0 and 1, right? And this is mostly water, right? 55 grams of ethylene glycol, 285 grams of water. We would expect that there's a lot more moles of water, so there's nothing that should scare us about that mole fraction. So that is the mole fraction for H2O, so 0.94670, and that gets multiplied by the vapor pressure of the pure solvent, 23.8 torr. .531. It's a good question. Does the unit of pressure matter? No, it actually doesn't. But whatever unit is used for the pure vapor pressure will be the unit that's on your partial pressure for your solution. Because this mole fraction is unitless, and so whatever unit you use here is the unit you end up with. It's surprisingly difficult to say. unit you use. It's too losing it. Okay, any questions? Okay, so what if the solute is volatile, meaning it evaporates easily? The solute then will also contribute to the pressure of the solution. Some solutions are ideal. They follow Raoults' law at all concentrations for both the solvent and the solute. And in that case, the total pressure is equal to the pressure of A plus the pressure of B. But you can also get non-ideal solutions. And these don't follow Raoults' law, either because the solute-solvent interactions are very strong or they're very weak compared to the solvent-solvent interactions. So 3 graphs. Here's ideal behavior, vapor pressure on the y-axis, mole fraction of A on the x-axis. So this is the partial pressure of component A in the red. So when the mole fraction of A is 0, its pressure is 0. And as the mole fraction increases, the partial pressure of that component increases until it gets to whatever the vapor pressure of the pure substance is. The other component is B. And so B over here, when A is at a 0 mole fraction, that means that B must be at a 1. So there's the vapor pressure of pure B, and that will decrease linearly until we get to 0 for the B. This is the vapor pressure of the solution. It's the sum of the partial pressure of A and the partial pressure of B. And this is ideal behavior. Everything works out nicely. If we have very strong solute-solvent interactions, meaning the solvent and the solute like each other a lot, stronger attractions, is that going to make your vapor pressure larger or smaller? Smaller. So what we see here is for component A, instead of being on this dashed line, being a nice straight line, we see that it actually dips down a little bit. The vapor pressure is lower than predicted by Raoults' law because these particles are liking being in the solution too much. They don't want to leave, and so the vapor pressure is lower. And the same thing happens with the other component. So then when we add these 2 curves together, we get this purple thing here, where the vapor pressure is actually lower in the middle than it is at either end. If you have very weak solute-solvent interactions, those 2 components are kind of pushing each other away. That will cause the vapor pressure of each to be higher than predicted by Raoults' law. And so then the curve bows in the other direction, and the vapor pressure of the solution also bulges up in the middle. So we aren't going to do any calculations with solutions like that, but you just need to have heard that they don't all follow the rules. Okay, so this problem is a bear. We're going to do it. Okay, a solution of benzene and toluene is 25% benzene by mass. At 25 degrees Celsius, the vapor pressures of pure benzene and pure toluene are 94.2 torr and 28.4 torr, respectively. Assuming ideal behavior, calculate the following. The vapor pressure of each of the solution components in the mixture. Okay. Well, we're going to use Raoults' law. It says assume ideal behavior, so we can assume that it follows Raoults' law. So let's look at maybe the benzene first because it's mentioned first. So the partial pressure of the benzene above this solution is going to be equal to the mole fraction of benzene times the vapor pressure of pure benzene. If the mole fraction of benzene was 1, then the partial pressure of benzene would be equal to the pressure for the pure benzene. And if this is 0, then the vapor pressure from benzene is 0. So we've got the vapor pressure, we need the mole fraction. All they gave us was a percent by mass. So we're going to have to take percent by mass and convert that into a mole fraction. So there are different ways you can approach this. Let's think about, well, what does 25% mean? That means 25 grams of benzene per 100 grams of solution, right? The mole fraction doesn't depend on how much of the solution we have. The mass percent doesn't depend on the amount of solution we have. We don't know how much solution we have, and it doesn't matter, but it's hard to calculate a mole fraction if you don't know how much you have. So we're just going to pick an amount. And if we're going to just pick something, we might as well pick something that's easy. So I'm just going to choose to say, what if we had 100 grams of solution? So I'll make a note of that up here. Choose 100 grams of solution. So there's that percent, and if I multiply that by 100 grams of solution, the grams of solution cancel out, the hundreds cancel out too. In 100 grams of solution, I have 25.0 grams of benzene. Just calling him B. Could I convert that to moles? Sure. Just need the molar mass of benzene. Grams, moles. Vague recollection of it being 78, but times 6 plus 1.008. Yeah, 78.108. So the grams will cancel out. Because to get the mole fraction, we need to know the moles of each component. So 25 divided by 78.108, 0.32006. Moles of benzene. How can we find the moles of toluene? So if we had 100 grams of solution and 25 grams was benzene, the rest of it must be the toluene, right? 100 grams minus 25 grams, 75 grams of toluene. You could also do that by thinking, well, if it's 25% benzene, it must be 75% toluene. Toluene is 7 carbons times 12.01 plus 8 hydrogens, 92.134. So 75 divided by that, 0.81403. Moles of toluene. Now that we have the moles of each component, we can find the mole fraction of benzene. So the mole fraction of benzene is equal to the moles of benzene divided by the total number of moles. The moles cancel out. 13.28222. Okay. What's the easiest way to find the mole fraction of toluene? Well, I could just replace the moles of benzene. I have two components in this mixture. Their percentages have to add up to 100. Their mole fractions have to add up to what? To 1. So the mole fraction of toluene equals 1 minus the mole fraction of benzene. It's 0.71777. So now I can find the pressure of benzene. That equals the mole fraction of benzene, 0.28222, times the vapor pressure of pure benzene. And those are listed in order, benzene and toluene. This is benzene, and that one's toluene. 92.4 or 94.2. .585 torr, and I'll do toluene down here in the corner. The partial pressure of toluene is going to equal the mole fraction of toluene times the pure vapor pressure, or the vapor pressure of pure toluene. 0.71777 times 28.4. $20.384. Any questions? So those would round to 26.6 torr and 20.4 torr. If we wanted the total pressure, we would just add them together. Any questions? Yeah? So that was part A of this question. We want to part B. The total pressure above the solution. Okay, well that's not so bad. So the total pressure will just equal the sum of the individual partial pressures. So I still have those heading in my calculator. 26.585 and 20.384. Add those together, we get 46.970, which rounds up to 47.0 torr is the total pressure. And then there's a part C. That was just, to lull us into a state of complacency or something. Calculate the composition of the vapor in mass percent. I had to think a while about this one yesterday. It was kind of embarrassing. This is challenging. So we have a vapor composed of two different components. We know they're partial pressures, right? And we know the total pressure. Ooh. Now I don't remember how I did it yesterday, but I just thought of I think it's a different way. So the partial pressure of a gas is equal to the mole fraction of the gas times the total pressure. And that's not toluene, that's total. So that's back from our gas law chapter 5 or something like that. So we know the total pressure, and, this is how I did it yesterday. And we know the partial pressure of benzene, so we can find the mole fraction of benzene in the vapor, which is not necessarily the same as the mole fraction in the solution. So the mole fraction of benzene is equal to the partial pressure of benzene divided by the total pressure. So the partial pressure of benzene was 26.585 torr, and the total pressure was 46.970 torr. So the torrs cancel out. Oops, that was a mistake. Try that again. The 26 divided by, oh my goodness. Having an argument with my calculator. No, 0.56600. That's the mole fraction of benzene. But that's not what they asked us for. They wanted the mass percent. In part A, we took a mass percent and went to a mole fraction. So we should be able to go the other way, right? Can we figure out the mole fraction of the toluene? The mole fractions have to add up to 1. So that's going to be 1 minus 0.56600. 0.433. Well, actually, I'll do it this way. Minus 0.566. So that's 0.434. Since those are zeros after that, we don't need to be writing those all over the place. So we got mole fractions. I want mass percent. So the percent benzene is going to be grams of benzene divided by grams of benzene plus grams of toluene times 100. Right? I can't quite understand you. So we're going to have to say we have a certain amount again. So we know that this fraction of the gas is benzene. So it might be easy to say, well, what if I have 1 mole of gas mixture? because we need it in moles because these are mole fractions. So I'm going to choose 1 mole of gas. And that's the mixture, both of them together. So if I have 1 mole of the mixture, that means I have 0.566 moles of the benzene, right? And I have 0.434 moles of toluene. Okay with that? Now, can I convert those to grams and plug them into my percent mass equation? Yes, I can. It's very tedious, but we can do it. Okay, so I'm going to start down here. 0.566 moles of the benzene. And I'm going to multiply by the molar mass. And that's going to give me 44.209 grams. There's no shortcut to finding the moles of toluene. I mean the grams of toluene. I got my moles of toluene there. I need to multiply by toluene's molar mass. It's hiding up here somewhere. 92.134. $39.986. Now I have the masses of each. So I can plug those masses into this equation. So 44.209 divided by the quantity 44.209 plus 39.989, 39.986, close parentheses times 100, 52.5. The percent for the benzene, now we can take a shortcut and just subtract from 100. $47.492. So we've got 52.5% benzene and 47.5% toluene. Yeah, it's a little ridiculous, isn't it? Why is the composition of the vapor different than the composition of the solution? Well, it sort of has to do with equilibrium. Does one of them evaporate more easily than the other? Yeah. Their vapor pressures are not the same, right? Benzene has a vapor pressure of 94.2. Toluene is 28.4. So even though the solution has a lot more toluene, its vapor pressure is significantly lower. So it contributes less to the vapor. Benzene contributes more to the vapor. and they come out being close to even. Any questions? Is this something you're going to see on an exam? I would not give you this on an exam. You might have part of this. You should at least be able to follow how I got where I got. A problem like this, I mean, like yesterday, I don't know, I brain fart or something. I was just like stumped. I had to pause and think out loud for a while, and we got it eventually. So the vapor pressure lowering happens at all temperatures. So we said that the boiling point of a solution, or of a liquid, was the point at which its vapor pressure was equal to the atmospheric pressure. So here is where it boils. If the vapor pressure is lower, then in order for it to boil, the atmospheric pressure is the same, it's going to have to get to a higher temperature. So the boiling point goes up, the melting point or the freezing point goes down. It has to do with the vapor pressure lowering. So because of vapor pressure lowering, the solution has a lower melting point and a higher boiling point than the pure solvent. So we have some very similar equations for these ideas here. Freezing point depression, the change in the freezing point is the molality times a constant. This is called, very concisely, the freezing point depression constant, KF. Molality is the unit used here, and in part that's because molality doesn't change with temperature. This delta TF, change in freezing point, is generally reported as a positive number, which goes against all the other trends we've seen, where it was final minus initial and the temperature going down should be negative. But here it's reported as positive. Sorry. So here's a table from your textbook. Here we've got several different solvents. Their normal freezing points, the freezing point depression constant. These are given in degrees Celsius per molal. And then just for a couple slides later, here's normal boiling points and the boiling point elevation constants, which are also in molal or degrees C per molal. So we're going to need the one for water in the next problem, 1.86. So calculate the freezing point of a 2.6 molal aqueous sucrose solution. So the equation is that the change in the freezing point equals the molality times the freezing point depression constant. So the freezing point depression constant for water, I looked it up on the previous slide, is 1.86 degrees Celsius per molal. And they gave me the molality. This is a nice change of pace from that last problem. Although sometimes it messes you up because you think, oh, it couldn't be that easy. And sometimes it is. 2.6 times 1.86. Oops, 4.836. Now this is where you can get a little messed up. What did I just calculate? The change in the freezing point. And what does the question ask for? The freezing point. This is an aqueous solution, so this is the change from the normal freezing point of water. If it was acetone or ethanol, I'd have to use their freezing point. So the normal freezing point for water is 0 degrees Celsius. And this is the change. Does the freezing point go up or down? That can be hard to remember. I remember struggling this for decades. I finally found a way to remember it. What happens is you add a solute and it pushes out the freezing point and the melting and the freezing point and the boiling point, so that the thing is a liquid over a larger temperature range. So boiling point goes up, freezing point goes down. So this change, I'm going down from 0. So I'm going to go down from 0, 4.836. And so the freezing point then, rounded, is going to be negative 4.8 degrees Celsius. Mm-hmm.
If somehow got a negative 4.8, would that mean the temperature's going up?
That's a good question. If you somehow got a negative here, would that mean that it went up? I suppose it would, except it's not possible to get a negative, because molality is always positive and the constant's always positive. See, if they had just put a negative sign on the constant, then everything would have been nice, but no. So boiling point is similar. Change in boiling point is the molality times a constant. So these two colligative properties explain why we don't use pure water in the radiators of our car. We use antifreeze, which is a mixture of water and ethylene glycol, or there's also some other substitutes now. The addition of the ethylene glycol causes the freezing point to go down and the boiling point to go up, because the radiator fluid is supposed to cool your car. Your engine gets hot, and if it gets too hot, it's very bad for it. So you need to cool it. So you've got this water running through the engine. Well, if the water gets up to 100 degrees, it begins to boil. And it expands, and it causes a lot of pressure, and that's where you get these billows of steam coming out of your radiator cap. If that happens, you should pull over right away. Do not open the hood. Just wait for everything to settle down, because you can get really badly burned doing that. So adding the ethylene glycol raises the boiling point of the water so that it doesn't do that. And then freezing, we don't have trouble with that around here, but where I grew up in the Midwest, if you just use pure water in your radiator in the winter, it would freeze solid. And when water freezes, it expands. And it can break lead pipes. I mean, it is just very powerful, and so it'll just break your radiator apart. But you add the ethylene glycol, and it causes the freezing point to go down, and so then you're not going to freeze solid. Any questions? So you can use pure water in your radiator in a pinch, but you don't want to just keep doing that. So we can also calculate boiling points. So calculate the boiling point of a 3.60 molal aqueous sucrose solution. So the change in the boiling point is equal to the molality times the boiling point elevation constant. So that's 0.512 degrees Celsius per molal, because I peaked as we were going through. So I knew I was going to need it. You just look it up in the table, or it would be given to you, perhaps, in the problem on an exam. So 3.6 times 0.512. Calculator says 1.8432. The units say degrees Celsius. Is that my boiling point? No. It's the change in the boiling point. Boiling point goes up. So I'm going to add that to the normal boiling point. The word aqueous here tells me what my solvent is. It's water. What's the normal boiling point for water? 100, right? So 100 degrees, and we're going up The change is 1.8432. And so our new boiling point is 101.8 degrees Celsius. Any questions? Another colligative property is osmosis, or osmotic pressure. Osmosis is the flow of solvent from a solution with a low concentration to one with a high concentration. And this is the process occurring that causes dehydration if you drink seawater.
Osmosis during the last slide with the cake plate and those two solutions with
Mhm.
that salty solution. Could it kind of like explain that a little bit? Or
Well, yeah, the water moving from one to the other, in that cake plate and two beaker situation, it's the same driving force as osmosis, but the difference there is it's going through the air instead of through a membrane. But it's doing it for the same reason. So, semi-permeable means partially permeable. It's permeable to some things and not others. So biological cells make great use of semi-permeable membranes to contain themselves and to allow interchange of all kinds of things, and they're very complicated and very cool, and the biologists can go study those. We make things a little simpler in chemistry, and so we make our own cell very primitive, I suppose. This is a U-shaped tube. We used to call them U-tubes. We can't call them that anymore. A U-shaped tube, and it has a semi-permeable membrane here. This membrane will allow water molecules to pass, but will not allow sodium and chloride ions to pass. So on this side we have a solution, say of salt water. There's a solute here. Over here we have pure water. What happens is the water can move back and forth through the semi-permeable membrane. And it's going to do that in both directions. When it moves into the more concentrated solution, well, let me back up a little bit. The rate of it going through is going to depend on how many water molecules are at that surface, roughly. And so here it's all water molecules, so they're going to go through. On the other side, the water is also going to go through in the other direction, but now there are solute particles that are in the way. And so the water cannot go back as easily. And so the result is there's a net flow of water from the pure water side to the higher concentration side. And that will keep going. Here we've got it set up so it's moving vertically, and as it moves up, it's also fighting gravity. So it will only go up a certain amount. If you did this more horizontally, you could get all the water to leave and go into the other solution. Here it's being opposed by gravity. We learned before that if you have a tube like this with different levels of liquid, that the difference in the heights is related to the pressure, right? So this corresponds to a pressure, and we define osmotic pressure as the pressure needed to prevent osmosis. So if you wanted this to go back the way it was, you'd have to put pressure on here. That's the osmotic pressure. It's the same idea here that of the mixing, the tendency towards mixing, the spreading out of, and the entropy, and that's the driving force. So we can calculate the osmotic pressure. This equation is a little different. It's like a yelling equation because it's all capital letters. So this is capital pi, capital M, capital R, capital T. M is the molarity, T is the temperature in kelvins, and R is the ideal gas constant. And we're going to use the 0.08206 liter atmospheres per mole Kelvin. So calculate the osmotic pressure in atmospheres of a solution containing 1.50 grams ethylene glycol in 50 milliliters of solution at 25 degrees Celsius. So the equation for this is capital pi equals the molarity times the ideal gas constant times the temperature in Kelvin. So we know what R is, liter atmospheres over moles times kelvins. And the temperature, 25 degrees Celsius, we add 273.15 to get the Kelvin, 298.15 Kelvin. But then we need the molarity. We've got a mass and a volume. What are the units on molarity? Moles per liter. So I need moles of ethylene glycol. They gave me grams. 1.50 grams e.g. Grams down here, moles up there. So one I screwed up on originally. I'm gonna have to do it again because my calculator won't go back that far. Okay. 2 times 12.01 62.068. Grams cancel. So 1.5 divided by that, 0.024167 moles. $50 milliliters. It is fine to convert this to liters in your head if you do it correctly. But a lot of times people say 0.5 liters is 0.05. So it might be safer to say, well, that's the same as 50.0 times 10 to the minus 3 liters, which is 0.0500 liters. So the molarity is the number of moles divided by the volume in liters. .48334 moles per liter. Imagine you were doing calculations like this for a big project at work, and your company would lose a lot of money if you screwed up. Would you just kind of punch numbers through in your calculator and come up with an answer, or would you write stuff down? You'd write stuff down, right? Because you're like, this needs to be right? There's a lot of money, maybe the safety of a bridge or something, who knows? You write it all out like this, and then you're going to show it to some other people and say, can you check my work? Can you make sure that this is correct? And they've got everything written out there, and they can check and find out if you made any mistakes. So is it important to get the answer correct on an exam? Yeah, so maybe you should write it out. And if you haven't been doing that, maybe you should practice. That's why I'm trying to get you to show calculations in your notebook. So molarity 0.48334 moles per liter times the ideal gas constant 0.08206 liter atmospheres per mole Kelvin. Okay, I'm done with that. And the temperature, 298.15 Kelvin. And look what happens with the units. The moles cancel, the liters cancel, and the kelvins cancel. Isn't that beautiful? When the units work out nicely like that, that's encouraging. It doesn't prove that you're doing it right, but it's encouraging.
How is this different from the ideal gas law?
That's a good question. How is this different from the ideal gas law? In the ideal gas law, we're relating the moles of gas and the volume of a gas and its pressure and its temperature. This really seems too simple to be true, that the osmotic pressure is equal to the ideal gas constant times the temperature times the molarity, which is moles per liter, and yet it is. So it's the purpose of the two. This isn't calculating the pressure of a certain quantity of gas. It's calculating the pressure to prevent osmosis. Make sense? They are very similar. Okay, so I've got my 0.4833 stuff times 0.08206 times 298.15. $11.825, rounding to 11.8 atmospheres. Yes?
Would it be a bad idea to cut down that polarity to 0.483 and multiply it?
It's a good question. Would it be a bad idea to not carry the extra digits? Let's see. So if I did 0.483 times 0.08206 times 298, you want to drop the 0.15 also? No? He doesn't want to drop it. That's okay. I get 11.817. So in this case, it's not going to affect the final answer. The problem is, if you round here, and you round here, and then you use this, and you round, and you keep using those numbers, it can build up. And the really awful thing is if you round this to too few sig figs. Like if I round this to 0.5, then I get 12.2 atmospheres. That's different. Any other questions?